barely hear you guys on the video. Yep. All right, so how do we go through and assign our oxidation states or oxidation numbers?
Known charges.
We have to go look for what's known. How do we know what's known when we're dealing with oxidation states? There's a list of rules, right? A list of ideas, a list of charges. Do you think you have to know that list? Yes, right? Otherwise you can't go through and assign these things. But remember, that whole list is based off of logic, right? There is a logic and a rhyme and a reason for how that works, okay? Remember, one of our rules says that your group 1A and your group 2A metals are always going to be 1 plus and 2 plus respectively. You guys already know how to assign those charges, right? That's what we did earlier with the ionic charges. So there is an overlap between ionic charges and our oxidation states or oxidation numbers, okay? Pay attention to the ones that might be a little bit tricky, like the hydrogen and the oxygen and some of these kind of weirdo rules that kind of pop up here and there, okay? All right. So let's just do one more here to knock the rust off. KMNO4. This one's a little bit different than the other ones on the page. Why? All the other ones are binary compounds. Here we've got a, isn't it ternary? Is that how it is? I think it is. That sounds good. Uh-oh, now we've got 3 things. Crap. Well, sorry, Dr. H, I can only do it for 2, right? 3 is for the advanced chemistry majors. What if we had 15 of them? How do you guys go through and assign these? You gotta go back and look at the rules, right? You find what you can identify, and you go back and you can assign what you can't identify. Every equation I give you guys in this class, right? I always have to give you enough information to solve for the unknown. Well, now we've got 3 components, so there better be information that you guys have about 2 of those, okay? We see our buddy potassium. Where's potassium on the periodic table? Column 1. Do we have a rule about column 1s? Yes, we do, okay? We see our buddy oxygen. Do we have a rule about oxygen? Yes, we do, right? So we have the rules for 2 of the components, so we use that to figure out the 3rd, right? What's important to remember is that everything has to add up to be equal to 0. How do I know that has to add up to be equal to 0? Because this is a neutral compound, right? There's no charge on that. Do I have to show you guys when there's a charge?
Yes.
Yes, I do, right? That's why I put the charges here and here, right? If there's a charge, I have to show that to you guys, okay? If I don't show you a charge, it's assumed to be equal to 0. Okay, so we've got 4 oxygens at -2. Okay. We've got 1 potassium at +1, right? A couple colors here. I ran out of room.
So manganese has to be +7.
Okay. Yeah. So then we have 1 manganese at X, and that all has to add up to be equal to 0, right? So 1, and then we have a -8, so +1 -8, right? So what does manganese have to be equal to? 7. Okay. What happens if I take 7 electrons away from manganese? Where does it end up?
On the other 2.
Hmm?
It sticks to the other 2.
No, I mean on the periodic table, right? So 1, 2, 3, 4, 5, 6. What happens if I take 7 away from manganese? What configuration, or where does it end up on the periodic table? Noble gas, right? Remember, that's one of these ways that we have of checking ourselves, right? So does it make sense that manganese would have a +7? Well, it seems to make logical sense. It would end up at one of these noble gas configurations, okay? So +7 for manganese, good? So hopefully you guys can go through and knock out the rest of those. I believe the next slide here was just more of the same, right? We've got another 3 component here, but we have a rule about hydrogen, we have a rule about oxygen, and all these kind of things that go into here, right? Lots of practice for these. Why? You have been using this a lot, okay? Not only in Gen Chem, but for those of you guys who are moving on to organic and to biochem, you guys will be seeing oxidation states a lot, okay? They're very important ideas.
Asabi.
Oh, no, this stuff's easy, right? Just got to do this. Okay, so now remember, we were learning this to be able to identify redox reactions. Okay, so if on an exam or a quiz I say, is this a redox reaction? You have to say, I better go through and assign the oxidation states for everything. Got it? So if I ask you guys to identify a redox reaction, or if I ask you guys to say, or if I ask how many electrons are transferred in a reaction, you better go through and assign your oxidation states. Because they're going to tell you what gets gained or lost along the way. Okay? So if we have this example here, right? We have S8 plus O2 goes to make 8 SO2. And I asked you guys, is this a redox reaction? I could ask you guys what gets oxidized, what gets reduced. I could ask you what's the oxidizing agent, what's the reducing agent. All these things come together. All right? All of those are asking the exact same question, I'm just using different terminology. To be able to answer any of those, you have to go through and assign your oxidation states. Yeah, what's up?
So can you know that it's a redox reaction without like doing like the oxidation numbers though?
No.
Okay.
Yeah, no with an asterisk. I would not recommend approaching it that way, right? That's a very easy way to kind of get tripped up, I would say. I don't know, Rachel, what's up?
How does this work if they both tend towards like gaining electrons? How does this redox?
It works the same way, assign your oxidation states. Just because you have a tendency to gain doesn't necessarily mean you're always going to gain, right? You're thinking about your ionic charges. So be careful with that. Right now we're working in the realm of oxidation states. They're not always going to be the same, right? Because we've got different sets of rules for how they work.
Okay, so oxygen is going to be the one that really wants to give its electrons up.
No.
Or gain electrons.
Yes. Yeah, and we'll learn why that is in just a couple chapters. Yep. Yeah, what's up?
Is the thing that's oxidized the oxidation agent, or the oxidizing agent?
Is it?
Reduction.
What does it mean to be a reducing agent? It's the agent that causes reduction. Okay? Causes something to get reduced. What does it mean to get reduced?
Charge to be reduced.
What does that mean though?
You gain electrons.
You gain electrons. So if you cause something else to gain, what happens to you? You have to lose, right? So that's why this gets tricky, right? So we have to remember, okay, if a reducing agent doesn't mean it gets reduced, it causes the reduction to happen, right? It's an agent of the reduction, okay? So real quick here, right? I gave you guys the answer, right? For both of these. The oxidation state for sulfur starts out as 0. How do I know that?
Because it's a pure element.
Right? There's two rules. Or excuse me, not two rules. There's one rule at play, there's one concept at play here, right? If we have S8, that's one of the elemental forms of sulfur. Now, how in the world are you guys supposed to know that, right? S8, how random. Okay, let's say we forgot about that, okay? Let's say we forgot about that idea. So ignore the zeros down there at the bottom. How could we figure out that the oxidation state has to be 0 on the sulfur and the oxygen? Well, we've got S8, right? What's the charge on S8? What's the charge on that molecule? It's 0, right? It's neutral, right? So everything has to add up to be equal to 0. How many sulfurs are there? Okay, so 8 times X has to be equal to 0. So what's X have to be? 0. You guys with me on this one? Right? So if you're having trouble figuring out, is this in something in its elemental form, just go through and assign the oxidation states. Okay? And you can do the same thing with oxygen on here, O2. Does that make sense?
So wait, if they're both neutral states,
Everything, no, there's 0 oxidation states.
right? So if they're both 0, then my brain's not.
Or maybe this is something new and we haven't quite let it marinate yet, right?
I think it's
Right? So both of these are in their elemental form, so we combine oxygen and sulfur, and we go to make SO2, okay?
Wouldn't that be a covalent bond?
It is a covalent bond. I didn't say that they have to be ionic bonds. I just said that we're doing oxidation states. So we're mixing a couple different ideas in here, right? I like the way you're thinking, but we'll have to come back and talk about that other stuff. We'll do this the same. Or just a couple of factors. So sulfur starts out at 0, oxygen starts out at 0, and they make SO2. Okay? So we assign the oxidation states to begin with. We assign the oxidation states at the end, 2 oxygens at -2, 1 sulfur, oops, crowding myself together here, 1 sulfur, okay?
Oh, okay, I get it.
Right, so the oxygen starts at 0, it goes to +4, write the X. Oxygen starts at 0, goes to -2, okay? What does that tell us? If I am oxygen, listen, if I am oxygen, and I start at 0 and I go to -2, what happened to me?
You got electrons.
I gained electrons, right? You guys with me on this one? Because if I gain an electron, what charge do I gain? A negative. Got it? How many electrons did I gain? 2. 2 per oxygen. Okay? 2 per oxygen. But how many oxygens were there to begin with? How many oxygens were there to begin with? Right, you guys with me on that? Right, so all these oxygens have to go through and the electrons got swapped, all these kind of, you guys with me on this? Oxygen starts at 0, based off of our rules, it goes to -2, each oxygen gained 2 electrons. If I gain electrons, what happens? I am reduced. Am I the reducing agent?
No,
No.
you're the
I'm the
oxidizing.
oxidizing agent. Reducing agents lose electrons. They get oxidized. So what's your reducing agent for this example? Well, what loses electrons?
Sulfur.
Sulfur goes from 0 to +4. Guys with me on that? How do I gain a positive charge? We'll have to lose electrons. If I lose electrons, I get oxidized, I am the reducing agent. So I cause something else to be reduced. This is confusing until you guys sit there and talk it through, right? You guys think I'm sitting here and just yammering on like this for your benefit, and that's somewhat true. But when I go through and I answer these types of questions, this is what I do. I talk to myself like a weirdo, okay? Why? Because I have to, right? That's why this stuff gets confusing. Otherwise, I just sit there and, well, I like oxygen, so I'm going to pick that as an oxidizing agent. Well, we need something a little bit more concrete than that, right?
So why is the term
Hang on just a second, Rachel. What's that?
So I understand there's rules, but
Yeah.
why is sulfur not negative two if they're in the same column or same?
Yeah. Good question. I will answer that in about, hang on to that thought for about 3 weeks. But that is the question, right? Because you're like, wait a minute, we learned this before, right? They're in the same column, right? We expect them to have the same charges, all this kind of stuff. I told you guys I lie to you all the time, right? You didn't believe me until now, right? No, that is the question. There's got to be another principle or property or something else going on. And we'll talk about electronegativity and orbitals and how and where the electrons actually go, okay? But don't get confused with ionic charges and oxidation states, okay? There is overlap between the two, but they're not exactly the same. And that's the tricky part, okay? Yeah.
So why is the term oxidized when it doesn't actually have anything immediately to do with oxygen unless?
It was a historical, it's a historical phrase. They used to think only oxygen caused this, right? They used to, I believe if I remember correctly, that it used to be defined as whether oxygen is added to or removed from something.
So is there, because of that initial observation, is there some sort of dynamic where oxygen is exceptionally prone to?
Yes,
fusion?
and that's the same question that Michael was asking.
Okay.
And I promise I will unravel that just a little bit, okay? Yeah,
I think this might be along the same line.
Yeah.
Why is the O go negative? Why not the X?
because you guys are all asking that, they're great questions, I promise. The answer is electronegativity and where the orbitals are, right? That's the immediate answer, and if none of that makes sense, it's because we haven't gotten to that chapter quite yet, okay? I promise I'll answer that as soon as we get to the chapter about the atomic structure, right? How we actually build an atom, okay? There's something more appealing to there's something more appealing to electrons about oxygen than there is sulfur. That's the simple way of saying it at the moment. And therefore the electrons are going to go hang out with the oxygen rather than the sulfur, okay? Yeah.
What is an oxidation number? Not
we could think of it kind of as a contrivance for us to track where electrons come from and go to, right? It's not necessarily that the oxygen has a -2 charge. It will be negative, but it's actually not gonna be a -2.
Track where they come from.
Yeah, it's basically to track the movement of electrons is what it is.
Got it.
Because what does chemistry at the end of the day, right? Electrons. Yeah,
I have one more question.
sure?
Is,
Are you sure it's just one more?
I-
I'm just kidding. What's up?
So, is sulfur solid and oxygen gas?
Yep.
Are those pure elements that are to zero?
Yes.
Yep. Okay.
All right. Anything else? Good questions, I love them, right? You guys are thinking about stuff, which is all I really ask. But it's tricky, okay? Tricky. Alright, here's what you guys did in lab. You guys took some copper, you mixed it with nitric acid, right? You dissolved up, you digested the copper. Right, you guys are doing a redox reaction. And you didn't even know it. Or did you? Oh, you did know. Ah. Right? So that's the reaction that you guys did, right? Copper with nitric acid. You guys can go through and assign all the oxidation states. I don't know, you might have to do that on your post lab or whatever. There you go, you got all the answers now, right? Okay? But that's what you guys are all doing. We're just transferring electrons from the oxygen, from the nitrogen, moving stuff around, blah, 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 making all these things, right? So, let's see what happened here. We start out with copper and its elemental form at 0, and ends up at +2. So what happened to the copper? It lost 2 electrons. So it got oxidized, right? Let's see, if I lose electrons, I am oxidized, right? Okay, so it was the oxidizing agent, right? No, it was the reducing agent, okay? So where did copper's electrons go?
It went to the others.
What others specifically? Copper had to lose 2 electrons. Where did they end up? To the nitrogen, right? Nitrogen started out at +5, it went to +4. Each nitrogen gained an electron. How many nitrogens are in our balanced equation? 2. You guys with me on this? So how do we easily answer any question about what gets reduced or gained or oxidized? What do you guys have to do for your equations first? Your oxidation states, okay? Gotta do the oxidation states. And then ask yourself the question I asked you, is it reduced, is it oxidized, what's the reducing agent, what's the oxidizing agent, what am I doing with my life, why am I here, right, all these things, okay? Impossible to answer questions. Assign oxidation states for your life, and then see what's happening. Okay, all right, you got it.
Is it possible to get donor brain cells?
Mm-hmm.
Seriously?
Sure. I mean, all you gotta do is find a brain, you can carry it around, right? So, here's a question. Because now you guys are in the redox mode. Is everything a redox? Yeah, what's up? I'm sorry.
How do you know where the how do you know which one goes to which one? Because you have so many different bits and pieces of elements, but then you all slam them together to their own little categories. So why not slam them together in different ways?
What way do you want to put them together?
I don't know, I can't really look at it because I have right now.
Okay. And I guess my question is also, I'm not really sure what you mean by slamming things together. It might, but you and I can talk about that, though, right? And then maybe we can hash that out, okay? So, not everything is a redox reaction, though, okay? So here we have a precipitation reaction. How do we know that this is not a redox reaction? What magic secret sauce do we have to do to figure it out?
Balance the electron stuff.
The oxidation states, right? So go through, let's assign some oxidation states real quick. I'll point something useful out to you guys. So real quick, what's NO3?
Nitrite.
Nitrate. Nitrate is nitrate and nitrate is nitrate. Do I have to assign oxidation states for that?
Yeah, we know the
nothing changed with it, right? Nitrate is nitrate, right? So if nothing changed, do I need to assign the oxidation state? No.
Well.
No, but knowing the ionic charge
Does it
helps.
matter then? So you have two.
Okay, don't believe me, that's fine. That hurt. I can't believe you think I'm gonna lie to you. That's fine. Don't believe me, go through and do it, okay?
Wouldn't knowing the ionic charge help you to figure out the ionic
Yes, it would.
oxidation state?
Yes, it would. Okay?
Are you just trying to trick us to make our lives sad?
Nope. I wouldn't lie to you guys about something tricky like this. Okay? But that's fine, you don't have to believe me. Right? So if we look at nitrate itself, the nitrogen's +5, the oxygen's -2, okay? We have 2 nitrates at -1 each. So what does that mean about the lead?
It has to be plus.
Okay. So there's the individual components in here.
Where does the K come from? Is the first K, is the K off being a typo?
No?
Oh, that's an I.
Yeah, that's an I, that's I.
Okay, it looks like an L.
Yeah, that might need to change the font of that. No, it's just a touch. Okay? What do we notice about things like Ki? Well, those are basically just our ionic charges in that case, right? But do we have a rule about the halogens? Do we have a rule that involves iodide?
Yes.
Yes, we do. What does the rule say though?
-4.
Typically, it's gonna be -1 with the exception of our,
The other ones are up.
the interhalogens, right? So it just happens in this case that the ionic charge is the same as the oxidation state. And that's what makes this tricky for you guys, okay? Is being able to parse the difference in between them, okay?
Does that rule mean like if we had an I and an F, it would just from the F?
The F would take the -1 charge, the I would take the plus in that case.
Okay.
Because fluorine has that, it's the same question that you were asking earlier about why does the oxygen take the minus off the sulfur? Same principle at work, we just have to learn what that is, that electronegativity on that. Yep.
If, sorry, nitrous oxide is, the out to be -1, why is TB +2?
Because the nitrates here, right? They're all equal to -1, so we have to balance it out with whatever the lead is.
And it goes with 2 nitrates?
Mm-hmm.
Okay.
Okay? We go through and quickly assign the rest of them then. We will find that lead is still +2 over here. -1 for the iodine.
And there's 2 iodines.
Mm-hmm. But we're always looking at an individual basis, per atom is how we break it down. +5 and -2, okay? So there's all the individual charges. So green for the lead, green is still +2. Purple +5 and -2, and it's still the same.
Hold on, why can't we just assume?
Don't assume. I'm gonna go ahead and stop your question there. But, go ahead anyway.
Is nitrite just counted as a single oxidation state because we know it's a polygon? Is this because the ionic charge is not the same as the oxidation, and so we can't like just count it as a single charge unit?
Yes, if I'm following what you're asking.
Like why write out +5 -2 instead of just writing out -1?
Because somebody didn't believe me that it stayed the same. So I'm just proving it to you guys. I don't know who, many people actually did, right? So you can just assume this is -1 because it doesn't change. It starts out as nitrate, it stays as nitrate,
Okay.
okay? But if you guys don't wanna do that, just write out all the oxidation states. You get the same answer, right? Okay? So, does anything gain or lose electrons here?
Nope.
Does the lead gain or lose? No. Does the nitrogen? No. Does the oxygen? No. Does the potassium, right? So if nothing gains or loses electron, is this a redox reaction? No. Okay, what type of reaction is it? Well, I gave you the answer up at the top. We mix an aqueous, and we make a solid. So this is one of our metathesis or exchange or precipitation reactions. Okay?
Do you ever get reactions of aqueous solutions that end up in one aqueous solution significantly more dense than the other, and it's hard to determine if it's precipitation? Does that ever happen?
Yes.
So at what point is the density identifiable as aqueous versus solid?
Good question. Hang on to that thought. I gotta keep going on this. Okay. And we could go through and we could figure this out here also. Some displacement reactions we found are redox reactions. I just assigned for the metals here, okay? Because if you'll notice, I got sulfate and sulfate. So again, we could build off of this idea of the polyatomics kind of staying as a unit. If you guys don't want to trust me on that, that's perfectly acceptable. Go through and assign oxidation states for everything, okay? You're going to find the sulfur has a +6 in both cases, okay? Yep.
Sorry, a question. Can you help me trust you? How is Fe 0? How is Ce 0?
What are the rules?
Pure element.
The other way, if you don't want to remember the rule, is this is a neutral molecule. There's one of them, so the charge has to add up to be equal to 0, right?
And we know it's neutral because you told us.
I did not put a charge there, right? Anytime, if I don't put a charge, don't assume that it's a typo, right? I usually don't make typos. Usually. Sometimes, hey, I'm not quite perfect yet, right?
If there's ever a typo on the test, it's gonna be a riot.
I don't, that's why I usually check myself pretty closely, right? All right, anyway, so what happened is that when chemists were first discovering this stuff, they noticed that certain displacement reactions, oh, I'm sorry, yeah.
Sorry, so for the SO4, since it's a polyatomic and it has a -2 charge, can you assume that?
Absolutely, yeah, polyatomic, those are something we can always, I wouldn't have you guys memorize those if they weren't something important that we can use as like a defined ionic part, yes, okay? So anyway, what happened is when they were going through and figuring out these redox reactions, this kind of stuff, they noticed that sometimes there was an exchange of electrons between certain metals, and sometimes there weren't, okay? So copper and zinc doesn't do anything, but copper and silver does, and iron and copper do some things here, right?
Well, and if copper and zinc were reversed, then they would react in this.
Yeah.
So why is that?
Good question. I'll answer the same way that I answered about the sulfur question that came up, and the oxygen, and all these kind of things. They're fantastic questions, and I promise I'll unravel the mysteries of the world to you, okay? But anyway, what they developed was this activity series. Now, we're going to shelve this for a little bit. We will come back to it in Gen Chem 2, okay, all right. Okay, so this comes down to if we can exchange electrons between metals, okay? We're going to talk about electrochemistry, and we do that in the second semester of general chemistry. Do you think it's important that we can exchange electrons between metals?
Yes.
Probably, right? Okay, why would it be important? Well, what batteries do you guys have in your laptops and cell phones, right? They're all these lithium-ion batteries, right? Lithium's a metal, and we can play off of its properties of wanting to gain or lose an electron, right? To be able to generate, right, a flow of electrons, and if we can move electrons, what do we call it? Civilization, right? Electricity, okay? Right? So pretty darn important, right? If you guys, you guys might have a car, right? What do you have in there? Well, you got a battery. What's the metal that's in your battery in your car? Lead, right? That's why it's extremely important for you guys not to go and just chuck that thing in the woods when you're done with it, right? You got a huge chunk of lead that's in there. It wouldn't be good to expose that to the environment, let it sit out there, right? So this principle of electrochemistry, these redox reactions are extremely important, okay? Extremely important. So we'll talk a little bit more about how to calculate how many electrons move between things and the charges that get produced from that, okay? But that's that activity series, all right? So what we need to know at the moment is how to assign the oxidation states and do the reduction, figure out what gets reduced and what gets oxidized and all that kind of stuff, okay? That's where we'll kind of leave that hanging for the moment. All right, so next major topic.
The Molarity.
Molarity, okay. Now, have you guys talked about molarity in lab yet? No, okay. So here's the problem. Now, since we're in chapter 4, we're dealing with how much stuff is in solution, okay? If I just put a pile of stuff on the desk in front of you, right? I come in there and I start scooping just carbon in front of you. You guys could take that over to a balance, right? You could get the mass, then you could convert mass into moles and tell me how many moles of that stuff there is, right? But if I dissolve something into solution, and you go and get the weight of that solution, you have what you dissolved plus whatever water it's dissolved in.
So you need the measurements of both dissolved and dissolved.
Correct, right? We need to know volume and we need to know moles, okay? And that's what molarity is, okay? It's gonna be tricky for you guys, I know, but all it is dealing with moles again, all right? Those stupid moles always coming back, okay? But that's all this is gonna be. We're gonna need to know how much stuff is dissolved, into what it's dissolved, and we're gonna use that to describe the molarity or something, okay? So if I say solute or solvent, there's a definition of those, and molarity is what we're gonna be talking about all along. Capital M is what molarity is, so if you guys ever see a capital M next to something, then that's the molarity of stuff, right? This is the same slide you guys had previously. This is just, you know, knocking the rust off of moles in case the rust had grown again, right? And here we finally get to the kicker, okay? So molarity is moles of what's dissolved per liter of solution, okay? Moles of what's involved per liter of solution. Do you guys know how to calculate moles of stuff at this point?
Yes.
Yes, you do, right? Can you convert moles into grams? Yes, you can, right? So the same math is going to be at work here. The only difference is we're going to have to deal with the liters, the measurement of volume that's there at the bottom, okay? Take note, it's volume of solution, not volume of solvent. A subtle but important idea to pay attention to.
Probably because of the dissociation, right? The dissociation causes a change in volume of the
Yes, it does, yeah. Right, it could either be positive or negative, and so we have to account for that, yep. Alright? So, how do I represent this to you guys? Right, there's a capital M that I was telling you about. If you see something in brackets, what I'm saying is you have a 1 molar solution of sodium hydroxide. You guys with me on this? So 1 molar solution of sodium hydroxide means I have 1 mole of sodium hydroxide per liter. Does that mean I only have to deal with liters? No. Does it mean I can only deal with 1 liter of things? No, right? The volume is what we decided to be, but the definition of molarity is per liter, okay? Just like when you guys drive your car, you measure things in miles per hour, right? Or miles per gallon, right? So it's a per something definition, just like we have here, okay? All right, we'll pick this up on Monday.
A drug?
See you around.
No, like,